In today's lecture, we're going to finish off Chapter 7 on heat considerations in nanoscience with a discussion of radiation. So remember that there's three mechanisms of heat transfer: conduction, convection, and radiation. Now we discussed conduction and convection in other lectures, so today it's radiation's turn. So this kind of radiation is often referred to, this kind of heat transfer is often explained by, I should say, black body radiation. So the idea here is that if you have an object sitting at any temperature, it's emitting radiation due to its temperature, just its temperature. Now, the amount and wavelength of the radiation emitted depends on the temperature of the object and the surface properties of the object. So the thermal radiation is really a continuous distribution of wavelengths from all portions of the electromagnetic spectrum, but it has a characteristic shape to the intensity curve, as we'll talk about here in a minute. Now, you might say black body radiation. What's a black body? What does she mean, black bodies? Okay, so here, a black body is an ideal system that absorbs all the radiation emitted on it. Okay, so a perfect black body has a perfect black body spectrum, as we'll talk about in a second. If you want a mental picture of what a perfect black body might look like, you might envision a black box with a little pinhole in it. Black is a color that absorbs a lot of light that comes in on it, and if it's only got a pinhole to escape, not much can escape. Now, a perfect reflector, I like to think of a disco ball, and that's the opposite of a perfect absorber. So a perfect reflector would reflect all light that's incident upon it and not really absorb very much at all. So the electromagnetic radiation emitted by a black body is called black body radiation. Now, as we've discussed, radiation doesn't require physical contact. It can be transmitted through a vacuum, just like the sun gives us heat energy. So all objects radiate energy continuously in the form of these electromagnetic waves due to thermal vibrations of their molecules, and that's black body radiation. Now there's a couple of equations that describe black body radiation. The first of those is Stefan's law, and it describes the transfer rate of heat by radiation. So the rate, or dQ/dt, the amount of heat per unit time, the power, P, is equal to sigma AE T to the fourth. Now, I'm sorry about all the sigmas. I know it's getting used for a lot of things. But here, sigma is not the conductivity. Instead, sigma is a constant that is associated with Stefan's law. And it's equal to 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. Okay? Now, A is the surface area of the object. Of course, if it's got a lot larger surface area, it's going to emit more thermal radiation. E is a constant called the emissivity, and that ranges in value from 0 for a perfect reflector, or disco ball, to 1, a perfect black body or a perfect absorber. And T is the temperature of the object in Kelvin, which of course you then raise to the fourth power. Now that's for a vacuum, like the sun hitting us. But if an object is sitting in a room or some kind of medium, then of course the heat transfer rate is going to be affected by the temperature of the background. So to compensate for that, you can alter Stefan's law in this way. The net power transferred out of the object would then be equal to sigma AE T to the fourth minus T0 to the fourth, where T0 is the temperature of the background. Okay? And then that'll give you the net energy lost or gained to an object via radiation. Let's do a quick example problem here so we can kind of cement these ideas in. The surface of the sun has a temperature of about 5,800 Kelvin, and the radius of the sun is 6.96 times 10 to the 8th meters. So calculate the total energy radiated by the sun each second, assuming it has an emissivity, E, of 0.986. So let's just use Stefan's law here. The power would be equal to sigma AE T to the fourth. Sigma is 5.67 times 10 to the minus 8 watts per meter squared Kelvin to the fourth. The surface area A of the sun would be the surface area of a sphere. So that's 4 pi r squared, which is 4 pi times 6.96 times 10 to the 8th meters squared. The emissivity of the sun was given to us as 0.986, and the temperature of the sun is 5,800 Kelvin, which we would then raise to the fourth power. And then that would give us a power of 3.9 times 10 to the 26 watts. And of course, that is the rate at which the sun is radiating away thermal energy in the form of blackbody radiation. Okay, so that's the rate of heat transfer via radiation. Let's now discuss the shape of the curve itself. So if an object's at room temperature, like, I'm pretty close to room temperature myself, the wavelengths of the thermal radiation emitted are mainly in the infrared region. But as the surface temperature of the object increases, the wavelength will also change. It'll glow red and eventually white, right? And then if you have a stellar object, sometimes you can even get radiation in the form of X-rays. So the peak of the wavelength distribution, lambda max, that shifts to shorter wavelengths as the temperature T increases. And that makes sense, of course, because we understand that shorter wavelengths are higher energy light. So this is known as Wien's displacement law, and the equation is a simple one. The maximum of the blackbody radiation curve, its wavelength, lambda max, times the temperature of the object is just equal to a constant. That constant is 2.898 times 10 to the minus 3 meters times Kelvin. So you can then simply figure out what the peak of your blackbody radiation curve would look like from that equation. Now, blackbody radiation curves, as I said, it's a continuous spectrum, but the spectrum has a characteristic shape, and it looks like this, okay? It has a steep left-hand side at small wavelength, and then a long kind of decaying curve on the right-hand side after the peak towards the longer wavelength side. Now, how do these equations that we've discussed fit into it? Well, the intensity increases with increasing temperature, and that's because the power increases with increasing temperature. So you can see the peak grows, right, as the temperature increases, and the amount of radiation emitted increases with increasing temperature, and that's the area under the curves here, right, as you can see. And the peak wavelength decreases with increasing temperature, so as it gets hotter, it gradually moves, right? So that's how that goes. So that's kind of a picture of what's going on with radiation at the macro scale, and that's generally what you learn in a 1000 level physics class, right? So basically, in order for heat to be transferred, the radiation is emitted from one object and moves to another. It strikes that object, and then the energy from that photon that hits that object is then absorbed in some way, and it becomes heat, right? So that's kind of what you learn about in a 1000 level physics class. Now that holds pretty well when the objects are separated by large distances, okay? That's a pretty good picture of how things go. But if you have small separations between the objects, and by small, of course, what I mean is nanoscale type separations between the objects, then things get a little bit more complex. See, the surfaces of materials actually have an energy of their own. They have all kinds of oscillations going on at the surface. We've already discussed plasmons briefly, but there's also another quasi-particle called the polariton. So these particles can form when light particles, photons, couple with other types of particles and quasi-particles. So remember, a plasmon is when you have a collective oscillation of the free electrons in a material. And so a photon, a particle of light, can couple to a plasmon in the following way. You have radiation coming in from the photon. Remember that a photon of light is just an oscillating electromagnetic wave. So you have an oscillating electric field, and then that oscillating electric field is felt by the electrons in the material, and it wiggles them back and forth. So you can have a coupling between a photon coming in and a plasmon on the surface, right? So you can think of them as photon-electron couplings, if you want. Now, a polariton is a quasi-particle, usually in an ionic crystal, and it consists of a photon that's strongly coupled to another quasi-particle, like a phonon or an exciton. Now, remember that a phonon, is the oscillation of the atoms within the lattice. It's wiggling. You can think of it like a sound wave, right? Where the atoms within the lattice are sitting there and wiggling back and forth. That's a phonon, and it can propagate through the material. Remember that an exciton is an electron-hole pair. Usually in a semiconductor, an electron-hole pair is created. So that's another quasi-particle. So it follows from the definition that there's a variety of polaritons, these quasi-particles, that can depend on the dipole carrying excitations. So there's a couple of common ones. There's phonon polaritons, and that results from the coupling of an infrared photon with an optic phonon. And there's exciton polaritons, and that results from the coupling of a visible light photon with an exciton. So these are some of the particles that are going on in the surface energies. So for example, let's think about this. If you have a large separation, here large just means 50 micrometers, basically you have these surface energies going on in either one of these surfaces, right? These plasmons and polaritons are wiggling their way around on the surface, but these materials are so far apart that it doesn't make any difference, and you just have energy transfer back and forth via these photons, basically our blackbody radiation that we've talked about before. But now let's take it and shrink it down so that you have the gap in between these two materials closing, right? Now at this point, some of these surface energy quasi-particles are close enough together that they can interact. And what that causes is a large jump in the heat transfer rate in between these two materials. See, now the whole story isn't just the photon transfer. The quasi-particles can transfer energy too, and that makes the heat transfer rate via radiation larger if the separations are smaller. So the plasmons and polaritons are much more dense near the surface of the object. Of course, they decay exponentially as you move deeper into the material, but these things can play a big role in heat transfer at short distances. When the two surfaces are close together, the surface polaritons and plasmons can interact with one another on those two surfaces, and this makes it easier for the photons to tunnel across from one to another. Okay? So you can have these particles interacting, causing more and more photons to be able to jump from one to another, and that makes the radiation larger. So how far apart can the surfaces be and still have this effect in play? Well, it's proportional to the wavelength of the light that you want to tunnel through. If it's due to heat transfer, of course, the dominant wavelength is going to be the one at the peak of the black body curve given by Wien's law. So you have to consider, where's the maximum of my curve? What's that wavelength? Now, if the separation in between is on the order of that wavelength, then you've got to think about it, okay? So what good is this? Well, heat transfer can occur more efficiently if this effect is exploited, and this might help prevent overheating in nanoscale components and parts. It could also be used to heat a surface purposefully with great accuracy if you want to do that. And why would you want to do that? Well, maybe you want to give something a kick and initiate a chemical reaction or something like that. And it could also be used to help make thermoelectric generators more efficient. Okay, well, I hope you found that interesting, and if you have any questions, let me know. I'll see you in class.